Okay, people, for our last learning goal in this module, I want to specifically get into this Joule-Thomson effect that we uncovered when playing with our relationships with enthalpy and changes at constant temperature or changes in constant pressure. So let's talk that out. So Joule wanted to repeat his original experiment that sought to measure deviations in ideal behavior as gases. And if you recall, that original Joule experiment failed mostly in its design, that it wasn't sensitive enough to measure those temperature changes, but it succeeded in its ability to rationalize what we expect for ideal gas behavior. So along comes William Thomson, aka Lord Kelvin. So those two people are one and the same. And Joule and Thomson were able to repeat something analogous to the original Joule experiment. However, they wanted to do it in a way that would give a meaningful result. So in other words, something that would be sensitive to very subtle temperature changes. And so the way that experiment worked, instead of having a static set of chambers where you just open, a high pressure chamber to a vacuum chamber and that's it, one and done. Instead, they envisioned this flowing experiment. So this is a flow of gases from one chamber to another chamber, and that flow is separated by a throttle or a very narrow opening. And so the idea here is, you imagine you've got a plug of gases flowing through. I know this shows it occurring like a piston, where this piston compresses and then makes the other side expand. However, we think of that as just a plug of gases flowing through constantly, okay? And so the idea here is that throttle is restricting the flow from one side to the next. And as it turns out, it's that flow restriction that allows us to measure this non-ideal gas behavior. So if we back up and look at what's trying to be measured, now this time they're going after mu, which we now call the Joule-Thomson coefficient. And recall that was the partial of T with respect to the partial of P at constant enthalpy. And if you design an experiment that's completely insulated, you will ensure isenthalpic conditions. And thus, for measurable changes, that will just be delta T over delta P, or in other words, T final minus T initial over P final minus P initial. So in this experiment, delta P is always negative, right? So the final pressure is always smaller than the initial pressure. And that's in part due to the throttle. So gases won't flow through this throttle smoothly. There will be a lag. So pressure will build in the initial condition. And typically in the final condition, it's open to the atmosphere. So PI is always greater than PF. Thus, delta P is always a negative quantity. So now what we look at in this experiment is, was there cooling or heating as a result of that expansion? And what can we conclude about their intermolecular forces? So if the Joule-Thomson coefficient is a positive quantity, then that means delta T was negative, right? So a negative makes a positive. And we would say that there are attractive intermolecular forces. So in other words, if the gases are experiencing real intermolecular forces, which they undoubtedly are, if they have to use their own energy to expand, right? Remember, this is adiabatic. There's no input of heat. The only input of heat is coming from the molecules themselves. So if the molecules cool upon expansion, they had to use their own internal energy to fuel that process. Thus, they must have had attractive intermolecular forces. Okay. Conversely, if the Joule-Thomson coefficient is negative, we can conclude delta T must have been positive, right? A positive divided by a negative is a negative. And so thus the gases will have warmed on expansion, and thus we can conclude that there was repulsive intermolecular forces. Or in other words, the gases in this initial high pressure state were crammed together. They didn't like it. They were, repelling each other. So they were able to have that benefit of expanding through the throttle and releasing heat in the process. Okay. So we can ask the question, is this universally true? Is it always true that some gases will cool upon expansion and some gases will warm upon expansion? And no, that's not necessarily always true. And we can also do a fantastic demonstration for this. So take your lips and purse them and blow on your hand. What does it feel like? Does it feel cool? Hopefully it does. And you can compare that to having your mouth wide open. And now I can feel the warm heat coming out of my lungs, right? So by making this throttle, I'm demonstrating this Joule-Thomson effect quite well. And hopefully what you can see here from the air that's in your lungs, it would have a positive Joule-Thomson coefficient, so it's cooling as it expands. Well, as it turns out, there is a range, or like a phase diagram, where gases can cool and expand. So for example, let's look at nitrogen right here. In this shaded region is the temperature pressure area for which we expect there to be cooling for nitrogen. And so on this scale, we're about right here for atmospheric pressure. And so if we go up to, around 300 Kelvin, there we are for nitrogen. So you can see we're square in the middle of the cooling area for nitrogen, and similarly oxygen exists in that range as well. So you can also see when we get outside of that range for nitrogen, we would expect heating, so the intermolecular forces flip. If we look at something like hydrogen or helium, these are the only two gases that will warm upon expansion at room temperature, right? So there, once again, is room temperature. And you can see for the hydrogen region and the helium region, we're well outside of that cooling zone. So hydrogen and helium will warm upon expansion. So I also like to point out, this is very cool, you can actually make liquid nitrogen by expanding it, not by compressing it. And that is, if you expand nitrogen gas from a high enough pressure into a low enough pressure, it will experience so much cooling that it will actually liquefy. So it's totally contrary to what you would expect, right? You would expect that we would compress a gas to make it a liquid, but under a certain condition, isenthalpic, or adiabatic, with a tight enough throttle, you could actually make a liquid out of something by expanding it, which is really cool. And there's a lot of modern refrigeration techniques that take advantage of the Joule-Thomson effect. All right, folks, that's it for this module. I'll see you in the next one.